Right, so let's look at question 1. It's all about Olympic athletes, and we're talking about forces and energy. So it says all forces arise from interaction pairs. So for every force acting in one direction, there's a force acting in the opposite direction. So which of the following conditions are needed for two forces to form an interaction pair? So first of all, each force has got to act on a different object, and the forces have got to act in opposite directions to start with, otherwise they're not interaction pairs, they're just resultant forces. So which of the following forces from a interaction pair is in this situation? Well, if we look at the actual picture, we've got obviously the athletes pushing on the beam that way, which means that the beam is also pushing her back up that way. So we've actually got a force acting in opposite directions. So if we look at the options, it's going to be the second one, the reaction of the beam that's pushing up on the gymnast, because the gymnast is also pushing on the beam. So we're now looking at the same gymnast, but on the trampoline. So let's have a look at what the question says. It says the gymnast has got a weight of 500 newtons. The trampoline does 250 joules of work when she's being launched into the air. What does this mean? Now, first thing we need to realise is that work done is equal to energy transferred. Okay, now that's actually given to us at the very front of the booklet. If we actually look here, the amount of energy transferred is equal to the work done. Okay, so if we look at the answers, put the tick next to the right one. It says the gymnast's weight increases. Well, that's not going to change a weight. Trampoline causes the force on the gymnast to half. Not the case. Gymnast pushes down the trampoline with a force of 250 newtons. The trampoline transfers 250 joules. Well, that is correct, because remember, work done. Right, so this is question II. I've already done the work and everything for this one. So we've got the height of the gymnast gains 250 joules of work being done on it. Now, obviously, this is going to be energy, because work done equals energy, as we got from the question before. So we can use the equation gravitational potential energy equals weight times height. If we rearrange this equation to get height on its own, it is gravitational potential energy divided by weight. So the gravitational potential energy is 250 joules that we get from the question here, and the weight of the athlete is 500 newtons, which we get from the question beforehand. So when we do that as 250 divided by 500, we end up with an answer of 0.5 metres. Right, so carrying on with question 1b, and this is III. The trampoline stores elastic potential energy when it stretches. Describe the energy changes. Now, a lot of us didn't actually talk about the energy changes as the gymnast moves from the top of one bounce to the top of the next bounce. So when she's at the top of the bounce, she's going to have maximum gravitational potential energy, because she's raised up off the ground, so she's going to have maximum gravitational potential energy. As soon as she starts to fall down, as she falls down, the gravitational potential energy is converted into kinetic energy. Okay, now that kinetic energy is down to the fact that she's moving. Gravitational potential energy is going to get less as kinetic energy is going to go up. When she makes contact with the trampoline, because the material is elastic, the kinetic energy is going to be converted into elastic energy, and that's because of the stretch within the trampoline. Okay, now this gravitational potential energy, if you imagine going right down to the bottom, it's then going to start pushing the gymnast back up. So this elastic energy is then going to be converted back into kinetic energy to move the gymnast back up. Okay, now as soon as the gymnast leaves the ground, or the trampoline starts to move upwards off the ground, this kinetic energy is going to be turned back into gravitational potential energy, so it moves right up to the top of a bounce, and then we're back at the beginning, and it'd loop round, so we'd end up with the whole thing starting again. Now, what we do need to remember is that energy cannot be created or destroyed. Right, it can only be transferred. Now, the fact that it can only be transferred means that there is going to be some energy lost, and that energy is going to be lost as either sound or as heat. Okay? Right, question 1C. It's slightly off the gymnast, but we're now looking at the forces within a moving object. So we've got a guy on a bike. He's travelling on a flat road. The forces are acting on there, so we've got a force acting up, down, left and right. The wind is blowing into the face of the cyclist, increase the cyclist to maintain the same speed. Now, it's dead important that we notice that it's the same speed, because if it's a constant speed, it must mean that the forces are balanced. Okay, so we've got actual balanced forces, so that means that the forces acting in all directions must be balanced. So, what it's asking us to do is it's asking us what would happen to each of the forces, the counter force. So the counter force is this force here. Now, it says in the question, the wind blowing in the face of the cyclist increases. So if you imagine that that force has increased, okay? So the counter force is obviously going to increase. The upward force from the ground, okay? Well, the vertical forces aren't going to change at all because he's moving on a flat surface, so that's going to stay the same. The driving force, the bit that's pushing him forward, well, it says in the question he's going to be maintaining the same speed, so the forces must be balanced. He starts to pedal harder to make sure that them forces are balanced. So that one is going to increase. The weight, well, the weight of the cyclist is not going to change, so that's going to stay the same. And then finally, the momentum of the cyclist. Well, momentum is equal to the mass times the velocity. So the fact that the mass of the cyclist is not going to change, it says that the speed is going to stay the same, so that is also going to stay the same.